In addition to output parameters like torque and speed, I'm also interested in things like motor power and efficiency. And so if I'm looking at motor power to start, I have an output power for my DC motor that's going to be related to my torque and speed. And I've added a little subscript M for motor torque because if I want to be accurate about this, that motor torque is comprised of both the load torque, that's actually the torque that I care about, so the torque that I'm applying to a particular load, plus perhaps some frictional torque that I have to overcome in my motor times my speed. So in my analysis here, I'm going to assume that that frictional torque is 0. So basically I don't have any losses due to that kind of frictional torque. So if that's the case, then my output power is going to be my torque times the speed in terms of torque. So this right here, remember, was my expression for speed in terms of torque, supply voltage, speed constant, resistance in the motor coil, and torque constant. So based on these motor parameters and my supplied voltage, I could get some power as a function of the torque that I'm operating at. But one of the things that we'll be interested in is finding the maximum power that I can get out of my motor. And so to find the maximum power, I'm going to set the derivative of this equation with respect to that torque equal to 0. So dp dt here is going to be Vs over Ke minus 2 times R kt Ke times T. So my torque at the maximum power is going to be equal to 1/2 Vs times Kt over R, which is 1/2 of my stall torque. And so if I take this torque at Pmax and plug it back into this equation, I can find my maximum power then is going to be 1/4 Kt over Ker times Vs squared. So one of the things that you can see from this is supply voltage is going to have a pretty big impact on my maximum power that I get out of my DC motor. And similarly, I can tease out of this that that maximum power is going to equal 1/4 times my stall torque times my no load speed. So this is a really nice thing to remember. So if I were to plot power versus my torque, and I could do the same thing with speed, right? If I put this all in terms of speed instead of torque, I could do the exact same thing. If I have a particular supply voltage that gives me some T stall here, that maximum power point is occurring at 1/2 of T stall. So this is T stall divided by 2. And this right here gives me some maximum power, P max, right? And so I'll obviously have 0 power if I'm operating at 0 torque, right? My power is going to be 0 when torque is 0. And I'll get something that looks like this, right? Because my power is also going to be 0 when my speed is equal to 0. So that's why I end up at 0 power at these extreme ends of this. And my max power is going to be right in the middle. Right, this is operating at some Vs, but let's say I go to a higher supply voltage than this and see what the effect is on power. So if I double my supply voltage, I'm going to double my stall torque. So now I'm at 2 times that original T stall, and in this case, I'm also going to quadruple my maximum power. So now my P max is something way up here, so that's effectively 4 times that original P max, and that's happening at 1/2 of 2 times T stall, so it'll happen right around here. So my power versus torque curve for 2 times the supply voltage, that original supply voltage, looks something like this. I still have that 0 power at the extreme ends of my spectrum at both my low load speed and my stall torque, right? But my power is going to increase increase quadratically with supply voltage here. And so this is one of the kind of key things to keep in mind if you're trying to drive a motor and trying to get very high power out of it. You're typically going to want to operate at 1/2 of the stall torque. That's also 1/2 of the no load speed, and you'll get a pretty nice maximum power at that point. For motor efficiency, I'm going to define that efficiency eta as P out over P in. And P out will be that load torque times my speed. My input power is going to be my supply voltage times my current that I'm shoving into that motor. And so this effectively equals that motor torque minus some frictional torque that I have, right? And this will be a little more important in the efficiency case because this is obviously leading to a decrease in efficiency, times my speed over that supply voltage times current. Right, I'm going to define an ILL as my no-load current, which is basically the current that I need to overcome that frictional torque. So TF in this case is going to be KT times INL. So I'm also, for convenience, going to define that motor torque, as I already know, as KT times my current. And I'm also going to define a stall torque as KT times that stall current. So my stall current is something that I'm defining in terms of stall torque, which I know is KT times VS over R. So equivalently, my I stall is going to be just VS over R. Okay, so using all of these, I can plug this back in to the efficiency equation. So my efficiency is going to be some KT times I minus that no load current, INL. That whole thing divided by VS times I, and then I'm going to multiply it by my equation for the speed as well. So that's VS over KE minus R over KT KE times my torque, which is KT times I. So if I do a fair amount of simplification here, canceling lots of terms, I make the assumption that KT equals KE, which is a little dicey because I've assumed some kind of friction in my system. So, some questionable assumptions in this, but to get a nice clean answer here, I'm going to get my efficiency is 1 minus my no load current over my current times 1 minus my current over my stall current. Right, by taking the derivative of this with respect to the current, I can find that my maximum efficiency is going to occur at an I is equal to the square root of the stall current times the no load current, and that maximum efficiency is going to be equal to 1 minus square root of the no load current divided by the stall current, that whole thing squared, or equivalently 1 minus the square root of that friction torque times my resistance divided by KT times VS, and that whole thing squared. So that's my maximum efficiency. So if I look at kind of an efficiency that I'm plotting versus a torque, if I have a stall torque somewhere out here, that maximum efficiency is going to occur somewhere quite different from my maximum power, right? And I could compute that based on this current right here times KT would give me that that torque at which I get my maximum efficiency. So right here, let's say I'm going to get a curve that looks something typically more like this. So that eta max, once again, is defined down here based on that no load current and that stall current and my torque constant, of course. So this once again gets into some interesting trade-offs that I'm not going to be able to operate at both maximum power and maximum efficiency at the same time typically. So my maximum power, remember, occurred at 1/2 of that stalled torque, whereas the maximum efficiency typically occurs at less than that. So typically occurs at a speed that's closer to the no-load speed and a fairly small torque. Finally, let's look at the idea of gearing on our DC motors. Oftentimes, if you have a DC motor, you're operating that with some kind of transmission attached to it. So I apologize for the gimpy looking gears here, but the key thing is that I have some gear turning some other gear. So maybe my output speed of my motor is my omega into the transmission, and the output from my gears I'm going to call omega out. And I can define my gear ratio that I'm going to call N as the ratio between omega in and omega out. So omega in, once again, is the input speed from the motor, and omega out is the output speed from the gearbox. So as a quick example of that, say I have a no-load speed of my DC motor of 1,000 RPM, and I'm given a gearbox with a 10-to-1 gear ratio, or I can think of this as N equals 10. So my no-load speed coming out of my gearbox is going to be that no-load speed coming from the motor divided by N, in this case 10, or just 100 RPM. I can also think about the gearbox efficiency, and that's going to be the torque at my output times my output speed divided by the torque at my input, effectively my motor torque, times my input speed, my motor speed. And this allows me to get a ratio of torques as well. So my T out over my T in is going to equal my gear ratio, N, times my efficiency. So if I have an efficiency of 1, my output torque divided by my input torque is going to be a factor of N. So if I decrease my speed by a factor of 10, I'm going to increase my output torque by a factor of 10. That's assuming a perfect efficiency. So let's look at what that means in terms of our torque speed curves once again. So let's say I have a no-load speed here, and I have some stall torque here for just my motor. So this is for my motor only. And now I'm going to I'm going to put a gearbox with a gear ratio of 3-to-1 on here. So my no-load speed is going to drop by a factor of 3 here. So this is my omega NL with my gears, and that's a 3-to-1, or an N equals 3 gearbox right there. My stall torque is going to increase by a factor of 3. So this is my T stall with my gearbox. It'll increase by a factor of 3, assuming that perfect efficiency. If I lose some efficiency, it doesn't quite go up by a factor of 3. So what I've done here is I've effectively changed the slope of my torque speed curve. Right? So by adding this gearbox and decreasing my speed by some factor and increasing my torque by some factor, I can effectively flatten out this curve. Right, which perhaps allows me to reach some torque speed combinations that I wouldn't be able to with the motor alone.